in the discussion. A few housekeeping notes before we start. The webinar is being recorded and will be made available afterwards. I think all your microphones and webcams should be muted. So these are turned off. If you've got any questions, you can type them into the chat tool and we'll get to them. We can answer them as we go, and then you can be unmuted afterwards to have a proper discussion. So yeah, there'll be time at the end allocated for the questions, but please ask them as we go, and we'll get to them if you know it's pertaining to what we're talking about at the time. If you're tweeting about this, please use the hashtag as shown, and it'd be appreciated if you can complete the survey afterwards. So the National Manufacturing Institute, Scotland, is a group of industry-led manufacturing, research and development facilities, where research, industry and public sector work together to transform skills, productivity and innovation to attract investment and make Scotland a global leader in advanced manufacturing. NMIS is looking to increase productivity by reducing barriers to innovation, looking to stimulate investment and increase manufacturing competitiveness, to catalyse job creation, strengthen the supply chain, and to increase talent and equip future workforces with skills that they need, and to work with manufacturing businesses of all sizes across multiple different sectors. You can see on screen here who NMIS is and who our partners are. And a slide here just showing what NMIS is physically. So I'm with the Advanced Forming Research Centre, along with the Lightweight Manufacturing Centre. We form the specialist centres, and then in development there's the rest of the NMIS makeup. So now on to the presentation itself. Can't stand the heat treatment, a bit tongue-in-cheek. Really what we're talking about is the potential of vibratory stress relief as an alternative to heat treatment. So I'm David Easton. I'm a Materials Knowledge Exchange Fellow here at the AFRC. I've been working in the area of residual stress for about 6 years. I lead the residual stress team at the centre. Salah, my colleague, he leads the overall materials and residual stress team. I did my undergraduate here at Strathclyde in aeromechanical engineering, and then a PhD with Strathclyde and Culham Centre for Fusion Energy. So the contents of today's talk is to look at why we need heat treatment. Why is it such a common process in manufacturing? Then to look at some of the drawbacks of heat treatment, some of the negative aspects that perhaps we'd look to find an alternative to. Then there'll be a section on vibratory stress relief, so an introduction to what VSR is, and then I'll look at the potential for VSR and what the scope and impact of this technology could be. So firstly, why do we need heat treatment? Heat treatment is a common process used in the manufacturing of many metallic and non-metallic components. There's a number of different uses for it: to relieve residual stress, to achieve particular microstructures, to generate specific material properties, or because that's what the specs say, it's how it's always been done and how it will continue to be done. Today, we're going to focus primarily on the need to relieve or reduce residual stresses. I'll come on to some of these other aspects a little bit later, but for the majority of this talk, we're focusing on the need to reduce residual stress and how that can be done. So residual stresses are an unavoidable reality of most manufacturing processes. In order to relieve these, heat treatment is applied. So basically we raise the temperature of the part, for example in a furnace, As the temperature goes up, the strength of the material reduces. If the temperature goes high enough and we're at temperature for high enough period of time, then the strength is low enough that the residual stresses are relieved, basically due to yielding. Then when you return the part to room temperature, you have a lower overall level of residual stresses. So before I go into more detail on heat treatment, I think it's worth taking a little bit of time just examining what are residual stresses and why are they important. So residual stresses are these stresses that exist in a part, where no external forces are applied. So once you've manufactured your component and it's just sitting there on the table, what are the stresses within that part? They exist within all real manufactured components. They're locked in stresses and all sorts of manufacturing processes affect them. They're often detrimental and unwanted, however, can be beneficial. They are compressive or tensile in nature, and this can be important in terms of if they're beneficial or detrimental. And they act across a number of different length scales, whether it's micro scale, mesoscale, or macro scale, as we can see here. To go briefly through some of the common sources of residual stress that we see here at the AFRC or that you're likely to see in manufacturing around the country. Forging, so whether it's open die or closed die forging, you've got severe deformation being imparted, you've got high temperatures, you've got temperature gradients, all of these result in stresses developing. Similarly with forming, cold forming or hot forming involves severe plastic deformation, again high levels of deformation and strain being imparted, resulting in high levels of residual stress. Machining, obviously a very common process, and machining itself can introduce residual stresses from the cutting tool, and can also reduce residual stresses as it removes material, leading to distortion. Heat treatment itself can introduce residual stresses. Here we're focusing on stress relief heat treatments, but that's only one of many. Prior heat treatments that could be applied to achieve a certain microstructure or material property, for example, will introduce residual stresses. Additive manufacturing, surface engineering, things like shot peening, and joining processes such as welding. All of these have the potential to introduce residual stresses into a component. You can see here just a diagram showing the different length scales that we're talking about for residual stress and all the different types that we can get, mechanical or chemical or thermal. It really is a broad range related to residual stress and why it's an important factor in so many manufacturing industries. Residual stress can have a significant impact on critical performance characteristics. So I'm not going to go out into much detail here in the model. We actually did a webinar last year taking a more in-depth look at residual stress, where you could find some more information on this. But it's enough to say just now that tensile residual stresses, for example, could have a detrimental effect on fatigue or on corrosion resistance, whereas compressive residual stresses could be used to improve fatigue. And any residual stress, whether it's compressive or tensile, desired or undesired, can result in distortion. And that's a particular focus for us here at the AFRC. So just to get a couple of specific looks at residual stress and why it's important that we relieve it in some circumstances. Gun barrels, so back in 1907, gun barrels would quite frequently fracture during operation. And then it was found that certain barrels actually weren't fracturing, and it turns out these were ones that had accidentally had their residual stresses beneficially modified. So this is an insight into how managing residual stresses can result in better performance. Similarly, if you fail to account for residual stresses, then catastrophic failures can occur, unfortunately. The Silver Bridge in Ohio, a single crack led to that crack propagating due to residual stresses, and many people died, which just highlights the importance for understanding residual stresses and then hopefully reducing them to a level that enables sort of safe operation. So for the reasons just discussed there, it's often necessary to apply heat treatment or an alternative process to relieve the residual stresses. However, it's not always plain sailing with heat treatment. There are some downfalls that we need to be aware of. So we'll move on to some of the drawbacks of heat treatment. So despite the benefits, there are a number of issues, and we'll run through these in turn. So environmental impact, cost, time, material properties and microstructure, size, and general material unsuitability. So from an environmental point of view, an unavoidable part of heat treatment is that you need a furnace at high temperature in order to heat up your part. In doing so, you can expend a large amount of energy. This is often done in large industrial scale gas furnaces or vacuum furnaces. So these are using energy, they're using gases and operate around the clock. So that's vast amounts of both energy and resources being used. The heat treatment of a single part may take an hour or two, or it could take several days or even weeks, depending on the part. So that can add up to a really detrimental impact in the environment. And in today's manufacturing world, where we're trying to move towards net zero and reduce these negative aspects, it's a definite negative side of heat treatment. In addition to the energy for the furnace itself, transport is a major concern. Whilst manufacturing is based all around the UK and the world, heat treatment is confined to localised areas generally, especially for specialised industries and applications, things like aerospace or nuclear. There's a limited number of heat treatment suppliers, and transport of parts to those suppliers, results in high uses of transport systems, high uses of things like petrol. And again, it's another detrimental contributor towards carbon. Cost. So heat treatment can be expensive. In pure terms, it costs money to pay somebody to heat treat your parts. This is often an outsourced aspect of the manufacturing process. It's expensive to get all the equipment required for heat treatment, and that's why quite often it's specialised suppliers that perform it. When we're talking about large or complex parts, the cost of even an individual heat treatment can run into the tens of thousands of pounds. And again, when we're talking about these larger, more expensive parts, or even high quantities of smaller parts, transport becomes a financial cost as well as an energy cost. And in some cases, the size of parts is just so large that it's prohibitive, whether it's financially or even just not possible. Heat treatment is sometimes ruled out. For example, bridges or submarine components, hydropower generation. Some of these components are giant, and getting a furnace big enough isn't always practical or financially feasible. Time. So heat treatment can take several days. We've gone over this already. I mean, it depends on the material and the component, but you it can be up to, say, a week to perform certain heat treatments. On top of this, you've got the aspect of control over timescales. If you're subcontracting your heat treatment, you're losing an aspect of control. So something like a gear wheel or a turbine blade, the heat treatment process time itself might only be a day or 2 days, but the total time could be several weeks when you factor in sending it to the heat treater, having them receive the parts, schedule it, perform the heat treatment, perform QA, and then return it. So it is a potential time sink. Material properties, this is quite an interesting one. So many components, especially for high performance applications like aerospace or power generation, or oil and gas, have tailored microstructures and specific material properties that they need. So for example, turbine discs, need to have certain fatigue properties. Hard weighting components such as bearings or gears need to be case hardened in order to get a high strength and a high hardness. These properties are achieved through thermomechanical processing typically. And now this can raise a problem when you then need to reduce the residual stresses, because using heat treatment, you're also relying on thermomechanical processing. And you could be restricted in temperatures that you go to. If you go to too high a temperature, you can change the microstructure, you could reduce hardness, you could reduce strength. And this can leave a real issue whereby you can't stress relieve your parts because you can't raise the temperature high enough to achieve it. And this is, I'd say, a fairly common issue that comes up in manufacturing. So all of these together ask the question, is there an alternative to heat treatment whereby we could get benefits? We could remove the residual stresses or reduce the residual stresses whilst avoiding some of these pitfalls of traditional thermal stress relief. The answer, potentially, is vibratory stress relief. So vibratory stress relief, or VSR, is a process whereby we look to remove residual stresses from a component without elevating the temperature at all. And the way that we do this is through the vibration of the component. So we've invested our time and efforts here at AFRC to acquire VSR equipment and to begin to look at the potential for how VSR can be used. So it's a process that has been used for decades, especially in heavy industries, particularly in the USA and in South America. However, the uptake hasn't been as high in the UK or in Europe and in some of the more advanced industries. So that's where we're looking to bridge the gap and see if we can better understand the process and better exploit the process in some of these applications. So VSR itself, it is achieved through vibration. So when we basically take a part of some sort, vibrate it at resonance or close to resonance, and through these high levels of vibration, we achieve stress relief through dislocation motion. This is an area that isn't as well understood as it should be. It's an area that we are looking at currently, and I think as we move to more safety critical applications for VSR, it's definitely going to be an area for research. The vibration is achieved through using an unbalanced motor, so it's dead simple. It's a motor that's out of sync, and we can go through a number of different frequencies and different vibrational amplitudes, and through that we can get the part to resonate. So for smaller parts, it's as simple as fixturing parts onto, say, a table, and for larger parts all we do is attach the vibrator straight on to the component itself. So it's much simpler perhaps in setup than some of the heat treatment. The key parameters we're looking at is the vibration frequency, the amplitude, and the time at resonance. So yeah, as I say, it's a small motor. It's very transportable. It weighs about 20 kilos. And with this rather small motor, we can treat parts that weigh, anywhere from a kilogram right up to, several tens or hundreds of tons. It really doesn't have an upper limit. I won't go into too much detail on the method itself. I mean, please, if you're interested in this and you think it's something that could be of use to you, I'm happy to answer any questions, and we can discuss this offline. But to boil it down to the essentials, what we do is clamp the workpiece, and then we do a frequency scan. So we're exciting the motor, and we're looking at how the part responds to all different frequencies. From that, we'll get a curve like we can see on the right here, and there'll be peaks at certain frequencies. So this is resonance. This is a natural frequency of the system. To do the treatment itself, all we do is set the motor to that frequency and basically spend an amount of time at that frequency, typically 15 or 20 minutes. And then we do a post-treatment scan to assess. So here you can see in green, which was the scan before VSR, and then afterwards the scan post-VSR. So if these two scans were the exact same, it would probably indicate that not much has happened. The stiffness of the system hasn't changed. However, in this case, we can see that some change has happened, and this is what would be qualitatively associated with a residual stress reduction. So that's a bit about VSR itself, and now looking at what are the potentials of VSR in industry. So all of these points here are basically relating back to the issues that we can have with heat treatment. So environmentally, VSR processing takes less than an hour per part. The energy consumed is significantly less. We're not heating up a big furnace and having to process gas or anything like that. It is plugging the machine into a typical plug that you get anywhere and running it for an hour. It's as low energy as it could be. Parts can be treated on site as well, so there's no need to transport heavy components all over the country. This is, again, particularly important for either large vessels, things like a pressure vessel or naval components. You can just treat it right there and then and reduce that transport. In terms of cost, the equipment itself costs £20,000 to £30,000. So this is orders of magnitude less than heat treatment equipment would cost. And in fact, a single VSR machine could be purchased for the equivalent cost of a single heat treatment of something like a large pressure vessel. Even when we're talking about more standard parts, turbine blades or something like that, you're not talking about too many cycles of stress relief before the economics of the VSR vastly outweighs the thermal. Time, again, the process time of VSR is likely much less than heat treatment. Perhaps more importantly is the fact that because VSR can be conducted on site and it can be conducted in amongst other manufacturing processes, you could, for example, do rough machining on a component say a gearbox or something like that, you could rough machine it, have it VSR treat it and have it back on for finish machining, within a few hours, rather than having to send it away for heat treatment and having it out of the process for days or weeks. So there is a real time benefit there. Again, material properties and the microstructure, you can have a number of materials that you're restricted for high temperature, especially things like stainless steel or aluminium or some titaniums. There is a real restriction on how high you can go temperature-wise to stress relief before you start to reduce strength or reduce hardness in particular. So by using VSR instead of the thermal process, you can preserve those microstructures or those material properties. There's no upper limit to the size with VSR, so things like nuclear power generation, this could be extremely important characteristics. And it can also open up the possibility to stress relief parts that just weren't possible before, and potentially expand the engineering capability of these parts. Additionally is the component unsuitability. So similarly to some materials not being able to be heat treated based on temperature, some components or systems of materials, so something like a dissimilarly joined structure, may not be heat treatable if you've got two quite dissimilar metals joined together. Perhaps one is high strength, high melting point, and one is lower strength, lower melting point. It's very unlikely that you're going to get an overlap whereby you can stress relieve at a temperature that's common to both of them. So in those cases, you would need to design around that inability to stress relieve or to have a less effective stress relief. And then if you use something like VSR instead, it could really open up the potential for the design of that component or for extending the operational sort of parameters of that component. So looking at the potential of VSR in industry, historically it's been used in large fabricated structures, things like hydro turbine machinery, naval components, press frames, machine tools, bridges, all these things, large engine blocks for things like off-road vehicles. So those are the standard use cases, and those are the ones probably with the most evidence in terms of successful application. Current uses of VSR that we're looking at and we're researching are things like aluminium, stainless steel, mild steels, different grades of Inconel and titanium. And we have a real interest in understanding the potential for VSR and residual stress relief and its fatigue implications on things like high strength aluminium alloys, high strength low alloy steels, basically all sorts of high strength materials that we typically work with at AFRC in advanced manufacturing. So I've talked a lot about the benefits of VSR. It's not going to be something that works in every scenario. There are some drawbacks, and we'll come on to some of the more challenging sort of components when it comes to VSR. But the types of components that would be a good candidate would be anything where machining distortion needs to be mitigated against. So the example I used where you could use VSR in between rough and finish machining, that would be a primary use case and one of the commonly used cases as it stands. High aspect ratio geometries, so anything with a low wall thickness or a high length, things like shafts, they will tend to resonate at a lower natural frequency and are therefore better candidates for VSR. Heavy and large components, again, the larger and the heavier a component gets, the easier it is to resonate. So that's good news in terms of being able to conduct VSR. It's also good news because these large, heavy components are usually ones that are costly in terms of finance or in terms of environmental impact to heat treat. So that's an area where a real impact could be made, if we're looking at net zero manufacturing, large vessels, large pressure vessels. These are the sort of parts where VSR could be used. And again, touching on the similar joint parts. As we move to the next generation of manufacture and designing more complicated geometries, designing multi-metal systems to be able to more effectively achieve the requirements of the part, the similar materials is going to become more common, and VSR could help alleviate some of the issues with stress relieving. So yeah, the inclusion of VSR really does offer manufacturers the opportunity to reduce environmental impact and move towards net zero manufacturing. It can also be part of the toolkit used to move from manufacturing for design to design for manufacture. As I've sort of said, with some of the special use cases and some of the more complex material systems, VSR really opens up the possibilities for stress relieving. And it's not always going to be a case of VSR instead of heat treat. The two could often be used in conjunction. And importantly, VSR offers manufacturers the opportunity to retain control of a key aspect of the manufacturing process. So you can reduce the time, financial and energy costs whilst maintaining more control. I think that's something most manufacturers would value. But there are, as I said, there are some considerations that have to be taken. And the most important one probably is effective stress relief. So what is the percentage reduction in stress relief that you're going to achieve? It should be said, heat treatment isn't always 100% effective. There's limitations in how far you can relieve the stresses thermally. And likewise, there's going to be similar limitations with VSR. So depending on the material, depending on the component design and geometry, some parts are going to lend themselves better to VSR and some won't. So it's not a one size fits all. But it is a potential option. Fatigue. So fatigue's an interesting one because generally if you reduce residual stresses, you're going to increase the fatigue life. Tensile residual stresses typically contribute towards lowering the fatigue life. However, there is the question of when you apply VSR, how much of that fatigue life are you using up by essentially cycling, at higher loads. So for high integrity components like turbine discs or anything like that, there's significant research that would need to be done to see what effect is VSR having on fatigue. And that's an exciting area that we look forward to working on. Again, repeatability. So likewise with stress relieving, using heat treatment, control over the process is always going to be important. Whereby with heat treatment, there's a degree of variability with where the parts positioned within the furnace, whether heating and cooling rates were maintained. And with VSR, there's going to be similar questions in terms of, is the clamping setup the same, as the operator, input the commands into the machine the same, and the same amount of time spent at resonance, for example. So it's a question that would have to be investigated, just like it is with heat treatment. So to summarise, residual stresses are an unavoidable and often undesired consequence of manufacturing. Thermal heat treatment is commonly used to relieve residual stress and has been for a long time. Despite this, there are downsides associated with heat treatment, primarily cost, time and energy. And if we look at VSR, this offers a real potential alternative to heat treatment. And in some circumstances, we can alleviate those downsides, and the cost, the time, and the energy doesn't become an issue. More research is definitely needed to truly understand the process itself, what is actually happening during VSR. And in addition to that, what is the potential scope for VSR? What industries, what parts can it be used on? And how impactful will that be? If we're talking about a high value component that maybe goes through 10 different heat treatment processes, can we completely replace heat treatment with VSR? Or can we replace a certain percentage of the heat treatments with VSR? These are the sort of questions that need to be answered. It's not, as I said, it's not one size fits all. It's not VSR is better than heat treatment or heat treatment is better than VSR. It's just a different alternative that in some circumstances could be highly beneficial. And in the spirit of the net zero manufacturing that this webinar series is focusing on, I think VSR is a strong candidate for improving the environmental impact of manufacturing. So yeah, as at AFRC, we're always looking to engage with anyone interested in this area, whether it's as collaborators or customers or future partners, or just anyone with a question. We look forward to engaging with you. And for anyone that's going to be around Glasgow in the next week, we do have our event on, as seen on the screen here. So that's all from me for just now, and if you have any questions for myself or for Salah, please ask away.
Thanks, David. There are a couple of questions. One of them is about size of the components. What are the limitations in terms of size, in terms of how big or how small they can be and shape? Yeah,
so in terms of how big they can be, there really is no upper limit. For large parts, all the process involves is attaching the motor or the vibrator to the part. So this could be bolted on or attached in some way, and then the part is positioned on some rubber pads to isolate it from the floor. So as long as you can move the part onto rubber pads, there is no upper limit. Because of the way the resonance works, as the part gets bigger, the natural frequency actually gets lower. So we're not relying on the motor to impart huge levels of vibration, because we're relying on the actual part itself reaching resonance, and that's causing the high levels of vibration. So that's one of the benefits. If you were looking at a different type of, so I'm talking about resonant VSR, there are other types of non-resonant VSR where size could be more of a limiting factor, but that's not the sort of area that we've been looking at. Probably of more concern would be the lower limit of parts. So anything under 500 kilos or say 700 kilos, the natural frequency tends to be high and beyond the frequency range of the machine itself. So if you were to attach the vibrator directly, we wouldn't get resonance, or we would only get one resonance peak. So to get around that, we use the setup that I showed earlier, where we have a high mass aspect of the setup. So we've got a T-slotted vibration table. I know a lot of the practitioners of VSR in the United States, for example, use the same setup, and then you just fixture the parts on. So it remains a question as to, does VSR become less effective on smaller parts if it's simply fixtured rather than being treated in isolation? But it's I wouldn't say there's any definite size restrictions for VSR.
Okay, thanks, David. There is another question from Paul asking about what type of microstructural evolution is happening during VSR, and more specifically, have you seen any measurements of dislocation behaviors during VSR? Or if you haven't done it yourself or you haven't seen, what is your suggestion to see dislocations evolution during VSR?
Yeah, so that's definitely one of the areas that we are currently looking at in our internal research program and with our research partners. In literature, there is evidence of dislocation movement. There's also evidence of retained austenite transformation, which that was one of the first observations. It was initially assumed that there was no microstructural changes, or certainly on the larger scale. However, in steels, the transformation of austenite into ferrite or martensite was witnessed. And then looking at some more of these papers, there is some focus on this dislocation movement that I've discussed. However, in general, a lot of people are attributing this as the mechanism without explicitly demonstrating it. So in our own work, we're looking to show this through comparing parts before and after VSR, for example, using EEM, something like that. But that's an area to look at in the future.
Yeah. Okay, thanks, David. A second part of the same question is about the effect of VSR on dual phase materials. You briefly hinted upon that during your presentation, but can you elaborate a little bit more on dual phase materials and what would be the effect of VSR?
Yeah, I think in terms of dual phase materials, from a titanium point of view, perhaps you would be better placed to answer, Salah. I'm not sure.
Yeah, so the simplest answer, Paul, is that I haven't seen any data on dual phase material, but theoretically, I think this, similar to many other work that David was talking about, it depends on material stiffness. So if you consider a dual phase material like Ti-6-4, for instance, since one is hexagonal, another phase is cubic, then I think, this is just purely speculation, by the way, I haven't seen any information, I think the stress relief in cubic phase is far easier than in hexagonal phase. This is just, again, a gut feeling. It needs experimental observations to back this up.
Yeah, and I think that's, touching on the evidence in general for VSR, it's something where the scientific evidence is less than anecdotal evidence, shall we say. So it's a process that is quite commonly used, as I said, especially in the United States. When VSR is used, machining tolerances can be achieved, and when it's not used, tolerances aren't achieved. So there is a clear benefit to using it. However, you know, being a research centre, we're looking to better understand the mechanisms for how that benefit's been realised, and to actually show it in black and white in a scientific format.
Okay, thanks, David. I don't see any further questions.
Well, if we don't have any more questions, then I think we can end it there.
That's great. Thank you very much, David and Salah, for your time today. And thank you, everybody, for attending and your questions. Please do feel free to get in touch with us if you'd like to take any questions offline. And a survey will follow shortly. We'd be most grateful if you could complete that to get your feedback for future events. Okay, thank you very much, everyone. I'm just going to end the webinar here. Thanks, David. Thanks, Salah.
Thanks, Salah. Thanks, Laura. Thanks, everyone.
Bye.